Alright, in this chapter, chapter number 11, we will cover acids and bases. Now, as you see in this image here, a standard soft drink will contain acids such as phosphoric acid, H3PO4, and also carbonic acid, H2CO3. This is a very common example of an everyday acid that we all encounter. Now, there are different types of acids. The first one we'll go over, Arrhenius. These types of acids will produce hydrogen ions, H+, when they dissolve in water. So the example that you're given, HCl, hydrochloric acid, dissolving in water, will give you the hydrogen ion, which is positive, and also the chloride ion, which is negative. And these types of acids are also electrolytes because they produce hydrogen ion in water. They tend to have a very sour taste to them. They also will corrode some metals, and they will turn a blue litmus paper red, and that's a good indicator that the substance that you're working with is an acid. Moving on to naming acids. Acids with a hydrogen ion and a nonmetal, or the cyanide ion, the Cn with a -1 charge, will be named with the prefix hydro, then end with the ending IC, or ic, acid. So for example, HCl, hydrochloric acid. Now, acids with a hydrogen ion and a polyatomic ion are named by changing the end of that name of the polyatomic ion. If the polyatomic ion ends with 8, it will be changed to the ending IC. This ion here, chlorate, if you add a hydrogen ion to it, you get chloric acid. If the ending of the polyatomic ion is ITE, that gets changed to OUS, and then acid. So for this example, this is chlorite. So if you add a hydrogen ion to it, you get chlorous acid. So all you're really doing is changing the ending either from 8 to ic or ite to us. Here's a table of some common acids and their anions. The acid HCl, hydrochloric acid, anion of course would be chloride, hydrobromic acid. All these are very, very common ones that you will encounter in any kind of chemistry class or chemistry lab. Alright, now we'll move on to a type of base, Arrhenius base. These will produce hydroxide ions, or OH-, when they dissolve in water. They have a chalky or a bitter taste to them. So B for bitter, B for base is a good way to keep that straight. These are also electrolytes because they produce hydroxide ions when they're in water. They will have a very slippery feel, a very soapy feel to them. They will turn litmus paper blue and the phenolphthalein indicator pink. The example that you're given here, sodium hydroxide, when it dissolves in water or dissociates in water, will give you the sodium ion, Na+, and also the hydroxide ion, OH-. So this type of base will produce a cation and then also the hydroxide ion. Now when it comes to naming bases, these are named as hydroxides. So NaOH, sodium hydroxide, KOH, potassium hydroxide. So all you're really doing is naming the first part of the compound and then adding hydroxide at the end. So barium hydroxide, aluminum hydroxide. Alright, next we'll move on to a different type of acid and base. These are the Brønsted-Lowry acids and bases. Now, according to this theory, an acid is a substance that will donate a hydrogen ion, H+, and a base is a substance that will accept a hydrogen ion. So this example here, hydrogen chloride, adding water to that, you get hydronium ion, H3O with a plus, and also chloride ion. So in this reaction, the hydrogen chloride will be considered the acid because it is donating the hydrogen to join up with water to form hydronium ion. And then the base would be the water. It is accepting the hydrogen ion in this example. Now in the reaction of ammonia and water, NH3, ammonia, will act as the base because it accepts hydrogen ion. And water will act as an acid because it donates that hydrogen ion. So here's the reaction. Ammonia, NH3, plus water will give you ammonium ion, NH4+, and also hydroxide ion, OH-. So in this reversible reaction here, water is acting as the acid. It is donating a hydrogen ion here to join up with the ammonia to form ammonium ion. So the ammonia would be considered the base because it is accepting a hydrogen ion. And because the nitrogen atom of the NH3 has a stronger attraction for hydrogen ion than oxygen would, water will act as an acid. That's why it's donating the hydrogen ion. Alright, now we'll move on to substances that are considered amphoprotic or amphoteric. Now these terms are related, but they're not the same thing exactly. They're not interchangeable terms. If a substance is considered to be amphiprotic, that means it's able to accept or donate a hydrogen ion. If a substance is considered to be amphoteric, that means it can act as either an acid or a base. So they are related, but they're not exactly the same thing. So for water, which is the most common amphoteric substance, it acts as an acid or a base depending on what it is reacting with. So water will donate a hydrogen ion when it reacts with a stronger base, and water will accept a hydrogen ion when it reacts with a stronger acid. So it just depends what the other reactant is will determine how water will behave. Alright, here's a good summary of water and how it could act in either way. If water accepts another hydrogen, it becomes H3O+, that is acting as a base. If it donates a hydrogen ion, it becomes hydroxide, OH-, and is acting as an acid. So it just depends on what is interacting with will determine how it behaves. Alright, now we'll move on to the strengths of acids and bases. Now, weak acids only partially dissociate in water. Anytime you see the term weak, we talked about strong electrolytes, weak electrolytes. Anytime you see the word strong, that means that substance will dissociate or break up completely. If you see the term weak, weak electrolyte, weak acid, weak base, that means they don't dissociate all the way. An example of that, hydrofluoric acid, HF, is the only halogen that will form a weak acid. So when this is dissolved in water, most of it will stay together, but you still get some ions breaking off. So it does form some acid, but a very weak acid. But for the most part, HF will stick together. A strong acid will completely ionize 100% in an aqueous solution. So hydrochloric acid, hydrogen chloride, gas plus water will give you hydronium ion and chloride ion. This is completely breaking up. That is a strong acid. But a weak acid will only dissociate slightly in water to form just a handful of ions, and for the most part it will stay together. So H2CO3 combined with water, you'll get some hydronium, but then you still get the bulk of what you get is HCO3-. So strong acid will break up completely, weak acid not break up all that much at all. Alright, for strong acids, in water, the dissolved molecules of a strong acid will break up completely, and you see the letters here, HA. H would be the hydrogen part of the acid, and A is a generic placeholder for the anion. So like we saw on the last example, or the last page, HCl plus water gives you hydronium ion plus chloride ion. So you get equal splitting here of those two ions. So over here, the strong acid HI, hydrogen iodide, plus water, it'll give you a nice even split. That is a strong acid. For weak acid, only a few molecules will dissociate. So the concentrations of the hydronium ion that are produced in the anion are really, really small. So for example, we talked about a few slides ago, HF. When that's dissolved in water, you get a great majority of the HF still intact, but you still get some ions produced. So this is a very weak acid. All right, in this table, you're shown the relative strengths of acids and bases. The first part of the table have the strong acids. As you get further up, the stronger they get. So hydroiodic acid is stronger than, say, nitric acid. The rest of this table are the weak acids here. And again, as you get from here going upward, you'll get stronger and stronger. And on this side of the table, you are given the conjugate base for each acid. The conjugate base is basically what is left over after the hydrogen ion leaves the acid. This example, hydrobromic acid. When you break apart this compound, if you take away the hydrogen ion part of it, you're left with the bromide ion. So its conjugate base is what's left over when you break up the acid. And as you get further down in the table, the stronger the bases get. The hydroxide ion would be a much stronger base than an iodide ion would be. All right, now we'll move on to strong bases. And these are strong electrolytes that are formed from the metals of groups 1A and 2A, and also include this list of compounds: lithium hydroxide, sodium hydroxide, potassium hydroxide, barium hydroxide, and so on. And because they're strong bases, they will completely dissociate in water. And these are found in very common household products, such as cleaners and things you'd use to unclog a drain. So, say Windex, Drano, Cheer, all those would have some very strong bases. Now, weak bases are weak electrolytes, and these will be very poor acceptors of hydrogen ions because they produce very few ions in solution. And a good example of a weak base is ammonia. So you have ammonia being dissolved in water. We'll give you ammonium ion a little bit and then hydroxide a little bit. But for the most part, NH3 will stay together. So again, anytime you see the terms strong and weak, whether it be in relation to an acid or a base or electrolyte, strong is always a reference to it being able to completely dissociate in water, and weak means it doesn't completely dissociate. All right, here are some common examples of strong and weak bases. Strong bases, lithium hydroxide, sodium hydroxide, and this whole table here. Some bases that are found in household products, both strong and weak. Window cleaner, Windex, ammonia, bleach, laundry detergent, toothpaste is actually has a form of a weak base inside it. Baking soda, laxatives, those are all have a form of a weak base inside. And a strong base that you would find in a household product, oven cleaner, drain cleaner. Alright, now we'll move on to dissociation constants for acids and bases. And what you see here is these are the ball and stick models of the compounds right above it. So this right here represents this ball and stick model, which is the same thing as this, HCHO2. And this ball and stick model is the same thing as CHO2 minus. And what the dissociation constant is a expression to show how much an acid or a base has been broken up within a solution. And those values will vary depending on each acid or each base and what they're being dissolved in. So it's a reflection of relative concentrations of the ions produced compared to the compound that hasn't dissolved yet. This dissociation of a weak acid, when a strong acid dissociates or breaks down in water, it is essentially a completed process. There's nothing left to do. So this is not considered to be an equilibrium process. But for weak acids, they only partially dissociate. So an example that you're given here, formic acid being dissolved in water will give you hydronium ion and formate ion. Because remember, this is a weak acid. It will not fully break apart, so you'll still have mostly formic acid left over, with some hydronium ion produced and some formate ion produced. And next we'll talk about the dissociation of water. Now this doesn't happen all that often, is fairly rare. But what you have is water molecules combining with each other and then quickly breaking down before they rejoin and form water again. So this is a reversible reaction. So you have two molecules of water here. They briefly will combine, forming hydronium ion, H3O+, and also hydroxide ion, OH-. But then these two quickly join together and form water again. So this process is not all that common. But you are still getting, technically, water being broken up and dissociated. For pure water, the ionization of water molecules produces small but equal amounts of both hydronium and hydroxide ions. And we look at the concentrations of both of those in pure water, you get this molarity, 1 × 10 to the -7. So they are both equal to each other. So pure water is a neutral compound. That's what's showing you here. Hydronium ion and hydroxide ion in pure water is a completely neutral solution. Now acidic solutions, so adding an acid to pure water will increase the concentration of the hydronium ion in that solution. So this will cause that concentration to go up, and also cause the hydroxide concentration to go down. So when you add an acid to pure water, you are forming an acidic solution. This concentration goes up, this concentration goes down. And the opposite of that will be true for basic solutions, also known as alkaline solutions. When you add a base to pure water, that will increase the hydroxide concentrations. It will also cause the concentration of hydronium to go down. But this solution would be considered a basic solution or an alkaline solution. Hydroxide concentration goes up when you add a base, and hydronium will go down. Alright, here are the last three charts all on one. We start off with a pure water solution, a neutral solution. Concentrations are equal to each other. When you have an acidic solution, hydronium ion will be much higher concentration. When you have a basic solution, the concentration of hydroxide ion will be higher. Alright, in this table you have the concentrations and the molar concentrations of various solutions. So for neutral, they'll be equal, 1 × 10 to the -7 molar for both. If it's an acidic solution, that value will increase, become more positive. So instead of being 1 × 10 to the -7 molar, you get an example of, say, 1 × 10 to the -2 molar. That's getting more acidic in solution. Same thing here. You are getting, because of the higher concentration, you are increasing this value. For solutions that are basic, you're increasing the hydroxide concentrations, so this value will go up. Instead of being times 10 to the -7, 10 to the -6, -5, -4, and so on. Now the way to measure the strength of acids and bases is what's called a pH scale. Now the pH scale ranges from a value of 0 to 14. A completely neutral solution like water is dead in the center at a pH of 7. Anything less than that is acidic. So 0 to 6 is acidic. And higher numbers, 8 to 14, are basic. And here's that sliding scale from 0 to 14. Like I said, the lower numbers will be acidic. The lower the number, the higher the strength in the acid. So an acid that has a pH of, say, 1.6, like gastric juice, is stronger of an acid than, say, coffee with a pH of 5. Really, really strong acids here. You get a little bit weaker, a little bit weaker, a little bit weaker. 7, which is neutral. Then going up, you get, these are weak bases, a little bit stronger, a little bit stronger. And the strongest bases are on the higher end. The extremes on either end are the strong acids or base. The strongest base would have a pH of 14. And you get a little bit weaker, a little bit weaker, a little weaker, really, really weak, and then neutral. So strong base here, strong acid here. And there's some common examples of what would be represented by various pH levels. Say a carbonated soft drink would have a pH of 3, oranges 3.5, coffee 5, urine is 6, that's a very weak acid. Dealing with bases, bile 8.1, seawater 8.5, bleach 12, sodium hydroxide 14, a very, very strong base. Right, because the pH scale is not just values of 1 or 0 to 14. It's a mathematical scale. It is a scale based on logarithms. So a change in 1 pH unit is actually a tenfold change in strength of acidity, or strength in the base. So even though the numbers sound small, say a difference between a pH of 2 and a pH of 3, that's a tenfold difference in strength. Then going from 3 to 4, that's another tenfold difference in strength. Even a small change in a pH value indicates a fairly strong change in strength. Alright, move on to reactions of acids and bases. Gastric acid, the acid found in your stomach, contains hydrochloric acid, which is incredibly strong. And this is made by the parietal cells that are found in the stomach. For hydrochloric acid, a pH reading of about between 1 to 2. And this is so strong it can give you a chemical burn if it touches your skin. So it's incredibly strong, which is what you would want for your stomach to help break down the food that you're eating. So as food enters the stomach, this hydrochloric acid is produced by these special parietal cells until the pH gets lowered to about 1.5 to 2. That's also why if you've had heartburn before, that's why it burns so bad, because you have the stomach acid that should be contained within your stomach leaking back into your esophagus. Right here. So that's why it's called heartburn. It actually feels like your heart is burning, but what's really happening is your esophagus is being burnt by the hydrochloric acid. Move on to reactions of acids. Now acids will react with metals to produce salt and also hydrogen gas. And acids will react with bases to produce salt and water. And acids will also react with bicarbonate and carbonate ions to produce carbon dioxide gas. And when I say salt, I don't mean table salt, sodium chloride. I mean the generic definition of a salt. So a salt is an ionic compound that does not have hydrogen ion as a cation or hydroxide as the anion. Here's some common reactions of acids reacting with metals to produce hydrogen gas and also the salt of that metal. Potassium plus hydrochloric acid will give you the salt of potassium chloride and then hydrogen gas. So this is the salt, not the compound salt, but a salt as a class of compounds, because there's no hydroxide as the anion or hydrogen ion as a cation. The metal zinc, when it reacts with hydrochloric acid, it gives you zinc chloride and also hydrogen gas. This would be the salt here. When you have acids reacting with carbonates and hydrogen carbonates, this will produce carbon dioxide gas and water and also a salt. So hydrochloric acid here reacting with carbonate will give you carbon dioxide gas plus the salt, calcium chloride, and also liquid water. The acid hydrochloric acid reacting with bicarbonate will give you carbon dioxide gas, the salt of sodium chloride, and then water. Alright, now we'll talk about when acids react with hydroxides, you'll get what's called a neutralization. In this kind of reaction, you'll get an acid reacting with a base to produce water and also a salt. And the salt formed is the anion of the acid and a cation from the base. So for example, a very strong acid, hydrochloric acid, reacting with a very strong base, sodium hydroxide, will give you the salt of sodium chloride plus water. So the anion from the acid here, and then a cation from the base. Alright, now we'll briefly talk about a very well-known indicator when it comes to chemistry labs. It's called phenolphthalein. Now this is used to indicate if a reaction has completed or not. And depending on what type of solution it's in, it will be a different color. So if phenolphthalein is in a solution that is acidic, it will be colorless. If it's found in a solution that has a pH of 8 or higher, it turns to pink. So this is a good indicator of a basic solution. Alright, now we'll talk about buffers. When you have either an acid or a base added to water, you will change the pH of that water dramatically. Buffer solution, what they do is they maintain the pH. So the pH doesn't change all that much whether or not an acid or a base are added. So for example, if you have a beaker filled with plain water, if you add an acidic solution, the pH will go down. So instead of being 7 like water normally is, if you add an acid, the pH will become more acidic. So it will go down to say 4. If you add a base, instead of being neutral at 7, it will go up, say to 10, 10.5. But with a buffer solution, when you add an acid, you get a very slight change, going from 7 to 6.9. If you add a base, you get a very small change the other way, 7.1. So buffers are used to minimize the impact of an acid or a base. And something like this is critically important when it comes to your body and digestion, for example. We talked about before on a previous slide how the pH of the hydrochloric acid in your stomach is incredibly strong, a pH of say 1 to 2. You can't have that kind of material entering the first part of the small intestine at that strength. It will just tear through the small intestine. So you have a variety of other chemicals, other enzymes, other buffers that are added to it to help neutralize it. So what basically happens is you have a very strong base added to that strong acid to help minimize the effect. Otherwise, you'll get ulcers within the small intestine. And buffers work because they resist the changes in pH from the addition of either an acid or a base. So in the body, they'll absorb the hydroxide ions or the hydronium ions from food or from other cellular processes, and various enzymes, various proteins that are used. Now this is important because it helps maintain the proper functioning of blood in various cells. The pH of your blood can only handle a very small window of change in pH. The pH of your blood should only be between 7.35 and 7.45. If it gets lower than that, you're going to have serious problems. If you have a pH higher than that, you're going to have some serious problems. So you have these various buffer systems that are used to maintain really tight window of pH that your blood can handle. Because if you have a change in pH of the blood, this will affect how well you take in oxygen to the cells. Now the components of a buffer solution will contain a combination of the acid-base conjugate pairs, a weak acid, and then a salt of its conjugate base, such as these. And will have equal concentrations of the weak acid and its salt. Now in the buffer with acetic acid, and here's the formula here, and sodium acetate, the salt produces acetate ions and sodium ions. This is what you get here. The salt is added to provide a higher concentration of the conjugate base, which is more than what you get normally from the weak acid alone. Here's that reversible reaction here. So acetic acid plus water gives you acetate ion plus hydronium ion.